Okay, imagine designing a skyscraper, one that can sway with the wind but, not crumble, or a super light aircraft, but it has to be, like, incredibly strong.
Sounds kind of like science fiction, huh?
Not quite. These impressive engineering feats are possible thanks to, well, our understanding of material properties, especially a concept we call elasticity.
Elasticity, right? That's how materials stretch and bounce back like a rubber band.
Yeah, it is. But it's much deeper than that. Think of a rigid steel beam. We
Hmm.
tend to think of steel as like unyielding, but even steel, it deforms under stress, even if it's microscopic. So that's where elasticity comes in. It's the material's ability to go back to its original shape after, the stress is gone.
Oh, so even the strongest materials, they have some give to them.
Exactly. And knowing how much give a material has, that's crucial for engineers.
Hmm.
And it's not just about like avoiding those big catastrophic failures, but it's also about, designing structures that can like flex and bend without breaking completely, like bridges that can, deal with heavy traffic and wind. That makes me think about those earthquake-resistant buildings. They're designed to sway during tremors.
Right. Exactly. They have to be able to absorb that energy, without falling apart.
Yeah.
And that's where understanding the elastic limit of materials becomes really important.
The elastic limit. So that's the point where a material stops being elastic and then it just kind of permanently changes shape.
Yeah, you got it. You stretch a rubber band too far past its elastic limit, it won't snap back. And the same thing happens with steel beams or concrete columns. If you go past their elastic limit, you can get permanent damage or, even the whole structure could fail.
So engineers need to know like exactly how much stress a material can handle before it hits that breaking point.
Absolutely. And to measure that, we use terms like stress and strain. Stress is the force on a material surface, and strain is, well, how much the material changes shape under that stress.
So like if I'm pulling on a rubber band, the force I'm using, that's stress. And how much the rubber band stretches out, that's strain.
Exactly. And the relationship between, stress and strain, that's where things get interesting. There's this really smart physicist from the 1600s, Robert Hooke, and he figured out a pretty simple but important law that governs this whole relationship.
Hooke's law. Right. I think I've heard of that. Didn't he like work with springs or something?
He did. So Hooke's law, it says that, within a material's elastic limit, stress is directly proportional to strain. Or, to put it simply, the more you pull on something, the more it stretches, but only up to a certain point, of course.
Okay, that makes sense. But how do we actually use this law, like in engineering and stuff?
Well, Hooke's law helps us figure out something called Young's modulus. It's a way to measure how stiff a material is. A higher Young's modulus means the material is it's tougher to stretch or compress.
So like steel would have a way higher Young's modulus than, say, rubber.
Exactly. And knowing this value is super important for engineers when they're choosing what materials to use for different things.
So it's not just like will it stretch, but how MUCH will it stretch under like a certain load?
Exactly. And that's why Young's modulus is such a basic idea in things like structural engineering, material science, even biomechanics. That's where we study the mechanical properties of, living tissues.
Wow. I never knew there was so much to learn about just elasticity.
Yeah, it's pretty foundational to understanding how materials behave. But, elasticity isn't only about stretching and pulling. It's also about how materials react to other types of forces, like compression and shear.
Compression, that's like squeezing, right? And what about shear? Isn't that like a sliding force?
Exactly. Imagine like spreading out a deck of cards. That's sheer force in action.
Yeah.
And just like with stretching, materials, they have different levels of resistance to these forces.
So are there different kinds of moduli to measure a material's resistance to those different forces?
You got it. There's bulk modulus, which measures how resistant a material is to compression. Think about it like a submarine. Its hull has to stand up to huge pressure from the water.
And if it has a higher bulk modulus, that means it's better at like resisting that squeezing.
Exactly. And then there's shear modulus, which measures how well a material resists shearing or twisting. This is really important for understanding how materials act in situations like earthquakes, where the ground is moving and creating intense shear forces.
It makes me think about, the San Andreas Fault, the tectonic plates grinding past each other. That must create some massive shear forces.
They do, yeah. And understanding shear modulus is super important for designing structures that can, handle those forces. For example, engineers use this knowledge to design buildings with features that let them move a little during an earthquake, absorbing the energy and preventing them from collapsing.
So it's not just about like being super rigid, but about designing things with like the right amount of give
Yeah.
so they could deal with those extreme forces.
Exactly. It's all about picking the right materials with the right combination of moduli to make sure the structure is strong and safe.
This is all so interesting. It seems like every part of how materials behave has its own like complexities and details.
It really does. And as we keep exploring materials, we'll find even more of these interesting properties. And we'll learn about the big effects they have on, well, on everything from everyday stuff to brand new technology.
I'm excited to hear more, but for now, maybe we should take a break. We've covered a lot, from the basics of elasticity to, how important these different moduli are in the real world.
Yeah, we've laid a good foundation for understanding how materials react to stress and strain. And when we get back, we'll look at another fascinating aspect of how materials act, how they respond to heat.
Welcome back to our deep dive into materials. So we've been like stretching and squeezing them, but now I guess it's time to turn up the heat a bit.
Exactly. Understanding how materials react to, changes in temperature is just as important as knowing how they handle, like, mechanical stress. Just think about it. Everything from bridges to even spacecraft experience temperature changes, and those changes can really affect how well they work, and how strong they stay.
It's funny you should mention bridges. It makes me think of those expansion joints, those gaps they build into bridges. It's to allow for like expansion and contraction because of temperature changes, right?
Exactly. That's a great example of how engineers have to consider this thing called thermal expansion. You see, most materials, they expand when they're heated and contract when they're cooled. It all has to do with how those, tiny little atoms inside the material behave.
So when you heat something up, the atoms start like moving around more, taking up more space, and that's what makes the material expand.
You got it. The hotter the material gets, the more those atoms vibrate, and the more space they need. And that's exactly why sidewalks have those gaps in them. It's to keep them from buckling when it gets hot out in the summer.
That reminds me of those old mercury thermometers.
Yeah.
The mercury heats up, it expands, and rises in the tube, showing you the temperature.
Exactly. It's a simple concept, but it works, right? It's a good application of thermal expansion. And, while most materials expand when they're heated, there are some exceptions. Believe it or not, some materials actually contract when heated.
Really? Wow. That's pretty strange. How does that even happen?
Well, it all comes down to the way the atoms are arranged inside those materials. Their molecular structures, they react to heat in, well, unusual ways, and that's what causes this, unexpected behavior.
So it's not always as simple as like heat it up, it gets bigger.
Not always. The world of materials, well, it's full of surprises. And to make things even more interesting, different materials expand and contract at different rates.
So even if you heat two different materials up the same amount, they might change size differently.
Exactly. And we use something called the coefficient of thermal expansion to measure these differences. It basically tells us how much a material's size will change for every degree Celsius that the temperature changes.
So a material with a high coefficient of thermal expansion would, I guess it would change size a lot more than a material with a low coefficient.
Exactly. And engineers, they need to know these coefficients so they can, avoid mismatches that could cause problems. Like,
Yeah.
imagine you're building a bridge with steel beams and concrete supports, but you don't account for the fact that they expand at different rates. Well, the bridge could crack or, even worse, it could collapse.
Wow, that's kind of scary to think about. So bridges, buildings, even spacecraft, all these things have to be designed with thermal expansion in mind, right?
Absolutely. And it's not just about, like, avoiding structural failures. Thermal expansion is important in all sorts of technologies. Think about bimetallic strips in thermostats or the precision engineering of microchips.
I've always wondered about those bimetallic strips. How do they work exactly?
So they're made from two different metals that are, like, bonded together, and each of those metals has a different coefficient of thermal expansion. When the temperature changes, the metals expand or contract at different rates, and this makes the strip bend. And that bending motion can then be used to trigger a switch, like to turn on your heater or air conditioner.
So it's just those tiny little strips using like the power of thermal expansion to control the temperature in our homes.
Pretty much. It's a simple idea, but a really elegant application of a basic material property. And the same principle is used in more complex things, too, like the design of microchips. Those tiny circuits are super sensitive to temperature changes, and engineers need to, very carefully control how much the different materials used in making them will expand.
It's really amazing to think about how something that seems as simple as thermal expansion can have such a big impact on technology and engineering.
It really does. But, while we're talking about heat, there's another thing we need to consider, the way that heat energy actually moves through different materials.
Oh, you mean like how a metal spoon heats up really quickly in a pot of hot soup, but a wooden spoon stays pretty cool.
Exactly. That's all about thermal conductivity, basically, how well a material conducts heat.
So some materials are better at like transferring heat than others.
Exactly. And it all comes down to the microscopic structure of the material, the way the atoms are
It
arranged.
makes me think about the difference between metals and, non-metals. Metals are really good at conducting both heat and electricity, right?
Right. Metals have this unique structure where their outermost electrons aren't tightly bound to their atoms, and they can move around freely throughout the material.
So it's like those free electrons are like tiny little messengers zipping around and carrying heat energy with them.
Exactly. They collide with other atoms, transferring energy, and that raises the temperature of the material. That's why a metal spoon gets hot so fast, the heat from the soup is quickly carried through the metal by those free electrons.
So what about things like wood or plastic? Why are they such bad conductors of heat?
Well, they have a different atomic structure where the electrons are, more tightly bound to their atoms. This makes it much harder for heat to travel through them.
So it's like the heat gets kind of stuck in those materials.
In a way, yeah. Their atoms can still vibrate when they're heated, but those vibrations don't spread as easily as they do in metals.
That makes me think of insulation. We use things like fiberglass and foam to keep heat from escaping our homes.
Exactly. Those materials are chosen specifically because they have low thermal conductivity. They act like barriers, slowing down the flow of heat.
So those insulating materials are kind of like the wooden spoon in the soup example. They resist transferring the heat.
That's a great way to think about it. Understanding thermal conductivity is super important for all kinds of things, from designing heating systems to, developing new materials with special thermal properties.
So it's not just about how a material will change with temperature, but also about how it'll move that heat around.
Precisely. And this is crucial for everything, from keeping our homes warm in the winter to making sure electronic devices don't overheat.
It's fascinating, really. It's like there's this whole hidden world of interactions between atoms that controls how materials behave.
There is. And the more we explore, the more amazing things we discover. Like, there's this really interesting concept called phase changes.
These changes, oh, you mean like when water turns to ice or steam?
Exactly. But before we jump into that, maybe we should take a quick break to let all this sink in. We'll be back soon to explore what happens when materials change their state of matter.
Welcome back. We've been on this journey through the world of materials, exploring how they stretch, bend, expand, conduct heat. But now I'm kind of curious about something we talked about a bit earlier, those phase changes. What exactly is going on when a material like shifts from one state of matter to another, like solid to liquid or liquid to gas?
Yeah, that's where things get really, really interesting. We're talking about, transformations happening at the molecular level, like changes in how those tiny particles are arranged and how much energy they have.
Okay, so let's stick with water as an example. We all know what exists as ice, as liquid water, and as steam. Those are its different phases, right?
Exactly. And what's fascinating is that during these changes, the temperature of the substance, it actually stays the same, even though you're adding or taking away heat energy.
Wait, so you're saying, like, if I've got a pot of water boiling on the stove and I keep adding heat, the temperature won't go above 100 degrees Celsius?
Exactly. That heat energy you're adding, it's not increasing the temperature. It's actually doing the work of, changing the state of the water, breaking the bonds between those molecules, letting them go from liquid to gas.
So the heat energy is like being used to transform the water, not just make it hotter.
Precisely. And this hidden energy, the energy it takes to change the state without changing the temperature, we call that latent heat.
Latent heat. So it's like this this secret ingredient that makes those phase transitions happen.
You could say that, and understanding latent heat, it helps explain a lot of everyday things, like why it takes longer to boil water than just heat it to, say, 60 degrees, or how sweating actually cools us down.
Oh, now that you mentioned sweating, yeah, I can see the connection.
Yeah.
When sweat evaporates off our skin, it's absorbing heat energy
Yeah.
and changing from liquid to gas, right? And that process is using heat from our bodies, which is what makes us feel cooler.
Exactly. Like nature's built-in air conditioner.
This is incredible. I never realized how much science there was behind something as basic as, sweating.
It's a perfect example of phase changes and latent heat happening all around us. And, these principles are used in all kinds of technology, from refrigerators to um, even advanced materials that use those phase change properties for specific purposes.
So speaking of different phases, is there a way to, predict what conditions will make a material switch from one phase to another? Like, how do we know when water will freeze or boil?
Right. Well, that's where something called a phase diagram comes in handy. It's kind of like a roadmap for a material, showing us the different phases it can exist in, depending on the temperature and pressure.
Okay, so it's like a visual way to see how those things affect the state of matter.
Exactly. Imagine a graph. Temperature on one axis, pressure on the other. Different areas on that graph represent the different phases: solid, liquid, gas.
So if you know the temperature and pressure of something, you can use its phase diagram to, figure out what state it'll be in.
Precisely. And the lines on the diagram, they show the boundaries between those phases. So, for example, the line between the solid and liquid regions, that represents the melting point. The temperature, where a solid turns into a liquid at, a certain pressure.
So if you're right on that line, the substance could be either a solid or a liquid.
Yep. It's in equilibrium, meaning both phases can exist at the same time. And there's this really interesting point on some phase diagrams called the triple point.
The cripple point, what's so special about that?
Well, it's the unique combo of temperature and pressure where all three phases, solid, liquid, A and D gas, can exist together.
Whoa, that's pretty wild. So at that exact point, you could have ice, water, and steam all hanging out together.
Exactly. It's a fascinating intersection of those different states of matter.
Well, so phase diagrams are like these secret maps that reveal not only the different phases, but also these hidden points of equilibrium.
That's a good way to put it. They're really powerful tools for understanding and predicting how materials behave under different conditions, which is, super important in all sorts of science and engineering.
This has been an amazing deep dive. We've explored those hidden forces that govern how materials stretch, compress, expand, conduct heat, and even change their state.
It's been a great exploration of material science, showing those intricate connections between, atomic structures, forces, and the incredible properties that come out of them.
And the best part is, we've really only just scratched the surface. There's still so much to learn, from, developing new materials with amazing properties to understanding the fundamental nature of matter itself.
Absolutely. So, stay curious, keep exploring. Who knows what amazing things we'll find in this fascinating world of materials.
Until next time,
Yeah.
keep diving deep.